Okay, we're going to move on to part 2 of our final exam review, and we're going to look at chapters 12, 14, and 18 to wrap this up. Chapter 12 is on chemical bonding and molecular shapes, and let's start off with distinguishing between ionic, metallic, and covalent bonds. Those are the three basic bond types, and when we look at this categorization, we first recognize that ionic bonds are between a metal and a nonmetal. A metallic bond is between two metals, and a covalent bond is between two nonmetals. With an ionic bond, the metal gives away its electrons to the nonmetal, and you have a cation and an anion resulting from that electron transfer. That's the key phrase to an ionic bond. The electron transfers from the metal to the nonmetal. With a metallic bond, you have atoms that are very deficient in valence electrons, and the few electrons that they have are loosely held. They flow around the nuclei in what we call the electron sea. Because of this, metals are conductive by nature. With nonmetals, you have small atoms. These are on the right-hand side of the periodic table, where atoms are small, but they also have a lot of protons in the nucleus. And the effect is that nonmetals are very good at holding on to electrons. So these are tightly held, and what we find is that the covalent bond is characterized by nonmetal atoms which overlap their electron clouds and tightly hold electrons between the nuclei. We call it electron sharing by electron cloud overlap. You should be able to identify a compound and the types of bonds it would have, and this leads to physical properties. So let's look at a few different compounds, and you can help to determine the type of bond it would have. We would then say if it has ionic bonds, it would have high melting point, high boiling point, would dissolve in water. Covalent bonds would be low melters, and metallic bonds which would be conductive of heat and electricity. Alright, here are some compounds for you. Let's look at carbon dioxide. Hopefully you categorize this as a covalent because you have a nonmetal and a nonmetal. Here's a metal with a nonmetal, K2O, potassium oxide. That's ionic. Then you see lead carbonate. Carbonate is a polyatomic ion. Lead sulfide ionic. Here we have sulfur with 4 hydrogens. This is all covalent. Now, hydrogen's an anomaly. It sits in both the metal and nonmetal category, but when it's with a covalent compound, when it's with a nonmetal, it's functioning as a nonmetal. This is covalent. And here we have metal-metal, so this is a metal alloy. Let's go through and assign polarity of a bond using the electronegativity values. Now, you do not have an electronegativity table on your resources guide, and so you would be given electronegativity values to calculate any type of polarity value. So if you look at if you would be given carbon's value of 2.5 and oxygen's value of 3.5, you would see that they differ by 1.0. So polarity is assigned on a continuum, and these are the basic cutoffs. If the electronegativity values of the atoms exceed 2.0, we call these compounds ionic. And if the electronegativity values differ by less than 0.4, we call these guys non-polar. And in the middle are the polar compounds. So considering this CO2 as a difference of 1.0, we would call it polar, but then that would be for the bond, but the overall molecule ends up being nonpolar because of symmetry factors. So the CO bonds are polar, but the overall molecule is nonpolar due to symmetry. For K2O, potassium has a polarity has an electronegativity value of 0.8 versus oxygen's 3.5. So we would definitely call this ionic. Here's an ionic compound. We already classify them as ionic. Let's look at SH4 and see if this is a polar or nonpolar covalent. Sulfur has an electronegativity value of 2.5, and that happens to be the same. Well, hydrogen's a 2.1, so we would call this nonpolar. And then we wouldn't assign polarity on a metallic compound either. Okay, so polarity is a covalent compound thing. So we have done this, and this is basically the same thing. We've done this, we've done this. All right, let's refresh our screen and look at the sizes of atoms versus their ions. When we have a chlorine atom, it has 7 valence electrons. It sits in column 7, so you know it has 7 in the outer shell. They are, it finishes with 3s2, 3p5. That's a chlorine atom. Chloride ion has picked up 1 extra electron to achieve the octet, and we have a way of indicating that with Lewis structures. We use a bracket and we put the extra charge out here, and this has achieved the noble gas configuration of 3s2, 3p6. It also has 1s2, 2s2, 2p6 preceding. And so looking down below, which of the following ions is isoelectronic with, we find that this configuration of 1s2, 2s2, 2p6, 3s2, 3p6 is isoelectronic with argon. And so by chlorine picking up 1 electron, it achieves this same stability of argon. It's not argon because, remember, argon has 1 more proton in the nucleus than chlorine. One more example of this, let's look at sodium. Okay, sodium has only 1 valence electron, sits like that. This has the electron configuration of 1s2, 2s2, 2p6, 3s1. Being a metal, it achieves stability by giving away that 1 electron and crossing that out. And so we have 1s2, 2s2, 2p6. So the isoelectronic question for sodium, what noble gas would sodium ion be isoelectronic with? It would be isoelectronic with neon. So when you get this question about isoelectronic, be thinking about noble gases. Atoms gain or lose electrons to achieve noble gas stability. Look for the noble gas that it becomes. Last comments with chapter 12. You do not need to draw any electron dot formulas, but you need to, in effect, to answer the question. So you'll be asked questions like how many lone pairs are in an oxygen molecule. All right, so let's look at a couple examples. If I give you SH2 and ask you how many lone pairs are here, you need to work this through. So sulfur has 6 valence electrons, and hydrogen comes in with its 1. So we would see this as sulfur having 4 electron regions around it, but only 2 atoms bonded. So on the shapes table it's a 4-2, which is bent. Or if you were asked the question of how many lone pairs, you would say 2 lone pairs. One more example. Let's consider PBr3. We put the least electronegative atom in the center. That'd be phosphorus. Phosphorus has 5 valence electrons. It sits in column 5. Bromines come along with their 7, so it would share first up, and then you'd have the 6 surrounding. So if you were asked shape, you would say there are 4 electron regions around the central atom and 3 bonded atoms, so you would say this is a pyramid. If you were asked the question how many lone pairs are around the central atom, you would say 1. Let's move into chapter 13, and we're dealing with molarity a lot in this chapter. What volume would you draw from 0.4 molar mother solution to make 100 mils of 0.15 molar daughter solution? Remember your dilution equation. M1V1 equals M2V2. And our mother solution is 0.4. Goes there. What volume? This is our X. We don't know how much to take of the mother solution, but we do know that our goal is to make 0.15, and we want to make 100 mils of it. So we know if we have milliliters on the right, then our answer is going to be in milliliters. When you solve for X, it's going to be 15 divided by 0.4, and you're going to get 37.5 milliliters. And sig figs wise, we really only have 1 sig fig, but about 38 milliliters. When you work problems out on the final exam, make sure that you're conscious of sig figs and units. Alright, if the solubility of cobalt chloride, now cobalt chloride, there are different charges possible on cobalt, and I was not clear. Let's just say we have cobalt 2 chloride. Cobalt has a mass of 59 and 2 chlorines have a mass of 71. So this compound has a molar mass of 130 grams per mole. Alright, if the solubility of cobalt chloride is 1.5 grams, will dissolve in 100 grams of water. Would a 0.2 molar solution of it be unsaturated, saturated, or supersaturated? Okay, remember saturated means that we have exactly 1.5 grams of the solid in 100 grams of water. It's right at its solubility point. Unsaturated means we're under that, or supersaturated means we're over it. So what we have to do is take 0.2 molar and convert that into grams per 100 grams of water so that we can compare if we're above or below 1.5. So how would you do that? Well, this is 0.2 moles of cobalt chloride in 1 liter of water. That's what molarity means. So I'm going to turn this top into grams, and I'm going to do that using that molar mass of 130 grams per mole. And then my top is in grams, and I'm going to get 26 grams on the top. That's in 1 liter, but that's not our definition. Now remember, a liter of water is a kilogram, and a liter is 1,000 milliliters, and so it's basically saying this is 1,000 milliliters. I need to get it, and 1,000 milliliters of water is the same as 1,000 grams, so I need to get it to 100 grams. So I want to move over 1. So I have in effect 2.6 grams. 2.6 grams of CoCl2 per 100 grams of water. Alright, and that means that we're super saturated. Okay, we're above the 1.5. In ocean water, what's the solute? The solute is the minority thing, which would be the salt, and the solvent would be water. So minority is the solute. State the conditions that increase the solubility of a gas in a liquid. Think about a can of soda. High pressure, low temps. Your soda goes flat when the lid's taken, or when you pop the cap, and when it's warm. Select the conditions that increase the solubility of a solid in a liquid. Okay, so what we found here was that high temp helped. High temp stirring, and then smaller particles. Okay, so you know how if you have a chunk of sugar in your cold iced tea, it doesn't dissolve well at all. But if you can use the little ground up sugar packets and warmer temperatures, you can get the sugar to dissolve really easily. Alright, predict whether the following compounds would be miscible, meaning they dissolve, or immiscible, do not dissolve, do not dissolve. In hexane, which is just a hydrocarbon. Okay, it's just a chain of 6 carbons all loaded up with hydrogens along the way. So that is very nonpolar. So you're going to just consider how polar are these multiple things here. So the first thing is ethanol. Look, it's got a lot of hydrocarbons. It has some polarity with this oxygen. This would be a polar hydrocarbon, but it should be soluble. And so we're identifying what is nonpolar here. Well, look, toluene is just a pure hydrocarbon, so that's a definite yes. Then we have acetic acid. We know that's a weak acid. See these oxygens there? It makes it slightly polar. And the ethanol also has 1 oxygen. So if we were to rank these things, we would say the C7H8 would be the most miscible. It's most similar to the solvent. And next, I'd put the ethanol. And that would be better than the acetic acid, which has even more polarity to it. And then lastly, this is something that is immiscible. You're not going to get an ionic compound to dissolve in a nonpolar solvent. So basically, just imagine this. Imagine you had vegetable oil and you'd throw salt in it. It would just sit in the bottom of the bottle. Alright, let's wrap up with the last 3 problems, which are molarity problems. What is the molarity of a solution containing 0.9 grams of NaCl? Well, the molar mass of NaCl, it's 23 for sodium, 35.5 for chlorine. So you get 58.5 grams per mole for NaCl. So we have 0.9 grams of it. So if you take 0.9 grams and divide it by 58.5 grams per mole, you're going to see that you have 0.0154 moles of NaCl. And you're going to put that in 0.1 liters. Okay, I'm immediately converting. 100 mils is 0.1 liters. And so your molarity is, if you divide by 0.1, it's like moving over 1 here. It's the molarity is going to be 0.154 molar. Sig figs wise, well, this has 3, this has 1. So it would be approximately 0.2. What is the volume of 0.2 molar HCl that delivers 0.05 grams of HCl? So really, molarity times a volume is moles. I've got to turn this into moles so I know how many I'm targeting. So HCl has a mass of 36.5 because chlorine's 35.5 and H is 1. So if I take 0.05 grams of HCl and I divide by 36.5 grams per mole, that's 0.00137 moles of HCl. That's how much I need to deliver. So the question is, what volume times 0.2 moles per liter equals 0.00137 moles. When you solve for x, you get x equals 0.00685, and that's going to be liters, right? Because I'm dividing through by moles per liter, and the liters will flip to the top. And so an easier expression of 0.00685 moles is 6.85 milliliters. And sig figs wise, I really don't have that many. I only have one sig fig, so you'd say it's about 7 milliliters. All right, last problem in this chapter. What is the molarity of an HCl solution prepared by diluting 500 mils of a 1 molar solution to make a total volume of 2.5 liters? All right, here's a dilution problem. So here's your dilution equation. And you're given 3 of the 4 things. You know your original solution, the mother solution, has a molarity of 1. You're going to take 500 mils of it. You're going to put it in another container. It's 2.5 liters, but don't make the mistake of mixing liters with milliliters. That's 2,500 milliliters. And then this is what we're looking for. If we do that, we take 500 of mother, put it over in a 2.5 liter flask, fill it to the line with water. What's the new molarity? It will be x equals 500 over 2,500, and that turns out to be 0.2 molar. And that's your solution. Okay? The solution to the problem, I should say. And we really only have one sig fig on that problem. Let's move on to chapter 14, acids and bases. All right, you really should commit to memory, and I actually should put this on the memorization list. Here are your strong acids. You have nitric, sulfuric, HCl, HBr, HI, not HF, and perchloric and chloric. All right, let's start chapter 14, acids and bases. Distinguish between strong and weak acids. First of all, strong acids by definition ionize 100%. By that we mean when this acid is put into water, it completely breaks up into H plus and the other thing. We'll just call it A minus. Okay? Likewise, strong bases completely ionize into OH minus and the other thing. There was some cation part of it. So, what are the strong acids? Let's just memorize these 7 strong acids. The number 1 strongest acid of all is perchloric. And then take away an oxygen and you get chloric. Then you should memorize nitric, sulfuric, and this series with the halogens, HCl, HBr, HI. Not HF. Okay, HF is a weak acid. If you memorize that, then you can distinguish. All right, the strong bases, column 1 metals with OH minus. So we're talking NaOH, LiOH, etc. The column 2 metals might be strong bases also. All right, which of the following would strongly conduct electricity. By that we mean ionize 100%, which is just asking which of these are strong. Is acetic acid on the list above? No. Is ammonia a strong base? No, just calm one metals with hydroxide. Is HCl on the list? Yes. Is NaOH on the list? Yes. Is HNO3 on the list? Yes. So memorize these 7 strong acids, know that column 1 metals with hydroxide form strong bases, and you're all set for these questions. Now we have a number of calculations for pH. Be very proficient on your calculator going back and forth on pHs and figuring out the hydrogen ion and hydroxide ion concentrations. Alright, what is the hydroxide concentration in an ammonia solution if the pH is 8.20? Alright, I can tell you right away you're going to have 2 steps, because when I reverse this pH 8.2, I will get the H plus concentration. It's going to be 10 to the minus pH. But I'm asked for the hydroxide, so I'm going to have to use a second relationship to get that. Well, anyway, let's get the H plus first. It's this. It's 10 to the minus 8.2. On your calculator, you could either do inverse log, or you could just go 10 raised to the negative 8.2. Make sure you use the change sign and not the subtract key to insert that negative, and you get 6.3 times 10 to the minus 9 molar. You know that's good because this 9 is similar to the 8.2. That's what logs are all about. They help simplify powers of 10. And you should always have an agreement when you reverse this 8.2 into its molarity equivalent. They should be very similar. Alright? Now, how do I get hydroxide if I know H+? There's a relationship that you need to finish this problem, and that is the fact that in water, the hydrogen ion concentration times the hydroxide concentration is always 10 to the minus 14. It's a constant. This is called the autoprotolysis of water. That said, I just figured out what H plus is. We just figured out that it's 6.3 times 10 to the minus 9. So I have one unknown in this problem. My hydroxide concentration will be 10 to the minus 14 divided by 6.3 times 10 to the minus 9. And when I do that, I get 1.6 times 10 to the minus 6 molar. Okay, molar is big M moles OH minus per liter. Alright, what is the pH if the H plus is this? Alright, so pH is minus the log of the H plus. These relationships here are reciprocals. They're saying the same thing. In this problem, because I'm given the H plus, I want to log it, and it will be a negative number, and I'll make it positive. pHs are positive. Okay, they're always positive. So minus the log of, and you're just going to put in your calculator the log of 6 zeros 1 5. Okay, when I do this, I should see something around a 6 or a 7. So I go log of, well, I don't put all those ones in. I would go 1.5 times 10 to the minus 7. And I'll get negative 6.8. And I make it positive. That's what the change sign is there in the front. Okay, 6.8. Next question, Bronsted-Lowry acids. Okay, this idea of Bronsted-Lowry acid, remember they are the H plus donors. And the Bronsted-Lowry base is the recipient of the H+. Okay, so you have to see what's happening over here. We see that this is actually phosphoric acid is reacting with water, and it's forming H2PO4 minus and H3O plus. Who's the donor here? This guy. This guy's the donor. It gives away its proton. See how that transferred the proton to the H2O? We would say the H2O is the Bronsted-Lowry base, and this is the Bronsted-Lowry acid. The last question is a titration problem question. All right, we've got an acid. The last question is a titration problem question. What is the molarity of an acid if 50 mils of it is neutralized by 27.5 mils of 0.15 molar NaOH? So go to your titration equation. MaVa equals MB VB, and I'm looking for MA. That's my desired thing. I know VA is 50. You don't have to switch to liters if you're consistent and you keep milliliters on both sides. Molarity of base is given as 0.15, and the volume of base is 27.5. So we're going to solve for molarity of the acid, and we get 0.15 times 27.5 divided by 50. 0.0825. And being consistent on sig figs, we get 3. So we'll say it's 0.083 molar. That's it for Chapter 14.